This video will cover the basics of the electronic fuel injection, or EFI system, and the role it plays in the operation of a Yamaha. The main function of any fuel supply system is to provide the correct quantity of fuel to match the amount of air going into an engine. This is referred to as the air-fuel ratio. This is not a fixed ratio because the engine requires different amounts of fuel as the operating conditions change. Some of these conditions include the temperature of the air and the engine itself, the altitude, and engine load. Note that these conditions can change a tremendous amount even during a single ride. For example, a rider could start off on a morning trip at low elevation with the temperature at 40 degrees, and as the day goes on and the ride progresses, the elevation could increase several thousand feet while the air temperature rises to the 80s or 90s. Along with these changing environmental conditions are operational ones, whether the rider is accelerating or decelerating, and the changing demands of the engine as it's being used, from a mixture that is rich at startup, then efficient at cruising speeds, and then rich again during acceleration. To meet these needs and achieve the optimum air-fuel ratio, many Yamaha models now have an electronically controlled fuel injection system that can constantly vary the amount of fuel to the engine instead of a conventional carburetor. Carburetor systems supply fuel through fixed-size metering jets and passageways and are usually set for the average temperatures and conditions plus a safety margin to handle short periods of extreme conditions. Since carburetors usually require various components be replaced to change the amount of fuel they deliver, the air-fuel ratio at any given time during operation is usually not optimum. An electronic fuel injection system provides highly precise fuel delivery, improved engine response, better fuel economy, and reduced exhaust emissions. The EFI systems used since 2002 on all Yamaha motorcycle, ATV, scooter, snowmobile, and side-by-side models are all very similar in basic operation. For instance, there are only 9 different sensors directly related to fuel injection, and of those 9, many models use only 7 or 8. The most important common element is the brain of the electronic fuel injection system, called the Engine Control Unit, or ECU. The ECU is a microcomputer with complete control over fuel and ignition systems, along with other engine-related functions such as the cooling system fan. And depending on the model, the ECU also controls many other functions such as the headlight relay, X-up system, or air induction system. The ECU monitors the various sensors for information on the performance of the engine, such as RPM, crankshaft position, throttle valve position, intake vacuum, and engine or coolant temperature. The ECU also monitors other sensors for operating condition information, such as air pressure, which equates to elevation, and air temperature. An important thing to keep in mind is that these sensors all operate on voltage. They do not send an actual temperature or pressure value to the ECU. For example, on the temperature sensors, air, coolant, engine, or oil, the ECU checks the DC voltage flowing through the temperature sensor circuit and refers to a chart of data that converts that voltage spec to an actual temperature reading. The ECU takes all of this information and then refers to a map to set the proper air-fuel ratio for those particular conditions. Instead of jets and passageways in a carburetor, models with EFI have fuel injectors, which are basically electrically controlled valves that spray fuel into each intake tract when they're energized by the ECU. The air-fuel ratio is determined by how long the ECU keeps the fuel injector energized. The longer the injector is energized or open, the richer the air-fuel ratio. The length of time that the injector is energized is referred to as the injector duration. If the ECU is the brain, then the heart of an EFI system is the fuel pump. This pump system supplies a consistent fuel pressure to each fuel injector. The real key to proper fuel injection operation is that the fuel pump system is designed to deliver a consistent fuel pressure to the injectors at all times. The specific fuel pressure setting varies from model to model and ranges from 35 psi on the smaller displacement models up to 56 psi on the big V-twins. All fuel pumps are designed to provide more fuel pressure than the engine needs and are equipped with a pressure regulator to set the specific fuel pressure for that model. Some systems have an external pressure regulator, which returns unused fuel from the fuel rail back to the fuel tank. This is referred to as a return type system. While other models use what's called a returnless system, which has the pressure regulator built into the fuel pump itself. in which fuel circulates in the tank and the desired fuel pressure is then provided to the fuel injector. When the ECU energizes and opens the fuel injector, the high pressure in the fuel system forces fuel into the intake tract as long as the injector remains open. The fuel is atomized by the extremely small openings in the injector nozzle and is sprayed into the intake tract as a fine mist. To decide the proper air-fuel ratio, the ECU needs to know how much air is going into the engine. This is mainly determined by three primary sensors: the throttle position sensor, or TPS, the crank position sensor, and the intake air pressure sensor. At lower engine speeds and throttle openings, the ECU determines the air volume based on the engine RPM and the atmospheric pressure and engine vacuum readings. At about 15% throttle opening, the ECU switches from using the intake air pressure sensor information and calculates air volume based on engine RPM and throttle plate opening angle. So the TPS, crank position sensor, and intake air pressure sensor, and these two calculation methods are used to determine incoming air volume at all engine speeds. With this information, the ECU can then accurately determine the proper amount of fuel to inject into the engine. Now, you may have caught a very important point here. The air volume is calculated, not actually measured. There are some fuel injection systems that actually measure the air volume, but most manufacturers today use this type of calculation method on modern fuel injection vehicles. This means air filter maintenance is critical, as well as only using approved service and accessory parts on the intake and exhaust systems. If any portion of the intake or exhaust system has some type of failure, not been maintained properly, or has been modified or replaced with non-approved parts, all the calculations the ECU does for air volume could be totally incorrect, and therefore the amount of fuel injected would also be wrong. As you know, the ECU controls the correct amount of fuel for the amount of incoming air by the length of time it keeps the fuel injector energized. The longer the injector is energized or open, the richer the air-fuel ratio. This is referred to as the basic injection duration. The ECU then makes small adjustments or compensations, either slightly increasing or decreasing the amount of time the injector is energized, based on the engine and air temperature, atmospheric pressure, and battery voltage. For example, cold air is more dense and therefore needs more gasoline to maintain the desired air-fuel ratio. So if the air temperature is lower, then the ECU slightly increases injection duration. And as you go higher in elevation, the air becomes less dense and needs less gasoline, so the ECU slightly decreases injection duration. As the unit is operated, the ECU is constantly monitoring the air temperature and atmospheric pressure to adjust the injection duration to maintain the desired air-fuel ratio. All of this calculation results in the final injection duration command to provide the proper air-fuel ratio for all operating conditions. Some Yamaha models now have a narrow-band oxygen or O2 sensor that has some effect on the final injection duration in specific conditions. These models are referred to as closed-loop systems, meaning that the O2 sensor sends information back to the ECU on whether the air-fuel ratio is rich or lean. Models without an O2 sensor are called open-loop systems. But be aware at certain times, closed-loop systems actually operate in open-loop mode. For example, after the engine is up to normal operating temperature, the XV1900 models operate in closed-loop mode only at idle and cruising speeds when the throttle is at a steady opening. In closed-loop mode, the ECU monitors the output voltage from the O2 sensor. If the voltage is on the high side of the range, the ECU determines that the air-fuel ratio is rich and slightly decreases the final injection duration. If the voltage is on the low side of the O2 sensor's range, the ECU determines that the air-fuel ratio is lean and slightly increases the final injection duration. All other times, such as engine warm-up on most models and accelerating or decelerating, the ECU ignores the O2 sensor voltage signal and strictly uses its pre-programmed map to determine the proper air-fuel ratio. Currently, there are 14 motorcycle and scooter models that have an O2 sensor, but only 3 different maps for closed-loop operation. Closed-loop mode at idle and steady throttle cruise, closed-loop only at steady throttle cruise or at specific engine speeds above an idle, and closed-loop during engine warm-up, at idle, and at steady throttle cruise above idle. So, as you can see, the voltage signals from the various sensors and computer processing by the ECU all boil down to 2 things. when to activate the fuel injector, and how long does it stay open. For more information on the O2 sensor, a detailed look at the operation of each of the fuel injection sensors and the self-diagnostic system, please watch part 2 of this video.